Now that we understand the full gradient descent algorithm, how can we know for sure that the algorithm is working correctly? Well, that's what we'll see in this video. We'll learn you how you can check that your gradient descent algorithm is working correctly and how you can debug it efficiently. Let's jump straight in. The most used tool to check if gradient descent is working correctly is by printing the value of the cost function in function of the number of iterations of the algorithm. So let's assume that our initial theta values give us a value for the cost function that is relatively large compared to the minimum. If we assume a problem where we only need theta 1, let's say we start out over here. If we now execute the gradient descent algorithm one time, we end up with some lower value for the cost function. We now just keep on repeating the algorithm until we reach the minimum of the cost function. And every step we take, thus every repetition of the algorithm, we plot the value of the cost function in a graph. So after some time, we might see a graph that looks like this. Now here we only assumed that we work with theta 1, but we can also extend this idea to a cost function with multiple variables. Now we might end up with a graph like this one. And this graph can give us a lot of insights into the algorithm. First of all, we immediately see if something is wrong. Because we know that gradient descent is working correctly if the value of j decreases on every iteration. So if we see a graph like this or this, we immediately know something is not right. It can be that there is something wrong with your implementation of the gradient descent algorithm, but in most cases, this is the result of the learning rate being too large. If you want to know how we can choose the correct learning rate, then I recommend subscribing as this will be the topic of next video. But first, let's get back to this graph. This graph is also very useful if the algorithm takes a lot of steps to converge. Because you don't know beforehand how many steps gradient descent will need to converge. In some cases it might be 100s, in other 1000s, and in some special cases it might run up to millions of iterations. So you don't want to wait for millions of iterations, only to see that there is something wrong with the algorithm. So what you can do is, you let the algorithm run for some time and plot its values in function of the amount of iterations. This way you can immediately see if it is working correctly. A second thing we can extract from this graph is that between 400 and 500 iterations, the value of the cost functions doesn't change a lot anymore. We can see that after 500 iterations the algorithm kind of converges. Of course we don't want to be estimating this from some plot. We want to implement this in software to know if the algorithm has converged. So we can check every iteration if the difference between the current value for j and the previous value for j is smaller than a certain threshold. This threshold is often denoted as tolerance or epsilon. If the change is smaller than this threshold, the algorithm is considered to have converged. The choice of the tolerance value depends on the specific problem, and it may require some experimentation to find a suitable value. Commonly used values for tolerance include 1 times 10 to the minus third and 1 times 10 to the minus sixth, but the appropriate threshold may vary based on the scale and nature of the objective function. A second method of checking if gradient descent is working correctly is to print the value of j and the value of the gradients and monitor its behavior. Some key points to look out for are: the value of j should decrease on every iteration. The gradients are becoming smaller as the algorithm progresses. Large gradients or sudden changes might indicate a problem. Keep an eye on the cost function and gradients for not a number or infinity values. These can occur due to issues such as overflow, underflow, or mathematical errors. By systematically going through these checks, you can often identify the source of issues in your gradient descent implementation. I hope this video was informative, and like always, if you have any questions, please leave them in the comments below.